Okay, so welcome back to Lean Together 2026. Next talk is by Thomas Murrill from the MathLib initiative, who will tell us about the better living through metaprogramming. That's exciting.
Thank you. So this talk, as stated, is better living through metaprogramming, solving the Goldblum dilemma with cotools. I'm Thomas Murrills. This is supported by the MathLab Initiative, a program of Renaissance philanthropy. So the Goldblum dilemma was introduced by Jeff Goldblum when he said, and I'm paraphrasing slightly, yeah, but your metaprogrammers were so preoccupied with whether or not they could that they didn't stop to think if they should. And this, of course, is from the seminal 1993 publication by Crichton, Cope, and Spielberg, in which certain suboptimal ramifications of a Goldblum dilemma that had been failed to be reckoned with were explored. So, what is the dilemma exactly? We want to do really, really cool things, right? We want to make dinosaurs, but they may come back to bite us later. So let me tell you first about these really, really cool things we can do. I think if you've been watching the talks in this conference, you hardly need convincing that metaprogramming can do really cool things. But let me tell you how. So Lean gives us quite a lot of artifacts that metaprogrammers can use to our advantage. So we start with the source file. From that, Lean creates really rich syntax objects that have all of the source info embedded in them. And from those, once they're elaborated, we create info trees in the course of elaboration. And info trees are essentially artifacts that save the elaboration process. So for example, if we have a certain identifier and it elaborates to a full constant that's an actual expression, that elaboration process is saved as a leaf in the info tree. And the reason I have the arrows pointing this way is that each of these refers to objects in the prior block. So info trees refer to specific elements of syntax, which they are the elaboration result of, effectively. And syntax refers to specific source items. And there's also a really important part of the Lean process I want to introduce real quickly, which is initialization. So it happens right after that red block of imports. And this is a time when Lean runs any IO action. So basically executes arbitrary code. And we can use it to add certain things to the environment. And it provides a really great hook for changing how we interact with the Lean file. For example, initialization is responsible for adding linters. So all of the semantically meaningful data that we get from Lean is nearly everything we might care about. And metaprogramming itself is sufficiently powerful to let us do nearly anything. So being able to do nearly anything to nearly everything is a recipe for some really cool capabilities. Now, you know metaprogramming is often used to create syntax annotation, tactics, linters, interactive suggestions, etc., even entire DSLs. But they can also provide library scale tooling, potentially, right? So we could be able to interact with our entire library at once. For example, we can modify source code in a syntax and elaboration aware manner because all of those artifacts are saved. And we can extract and analyze meaningful data. And we can do it all interactively. So, okay, let's explore now how those programs might come back to bite us later. So, okay, first recall that libraries are alive, right? They persist through time, they evolve, they change in their design and their needs and the scope, and they also depend on things that change. And the overall challenge of keeping what you've got amid these changes is called maintenance. Metaprograms can often be more powerful at the price of being cursed, which is, needless to say, bad for maintenance, but let's get into exactly what this means and how. So the definition I came up with was something is cursed when it puts together pieces which are unintended for a given task and or relies on happenstance coincidences among those pieces, so on implementation details. So a cursed metaprogram might therefore be hard to understand or arcane. It might be really hard to change, whether we want to extend it to do something else or fix it or refactor it. So it might get ossified. And it might break often since these coincidences we're relying on were never actually promised to us and they're fragile. And all of that is, of course, a nightmare for maintenance. It's also very easy to do. So metaprograms can grow very complex and cursed very quickly. It's a testament to how powerful metaprogramming is, but there are a few automatically enforced invariants. Great for flexibility, but we can violate them whenever we please. And so the act of respecting them demands knowledge of us, demands us having an awareness of what those invariants are and how to respect them. And each new powerful metaprogram might need to access really arcane parts of Lean to get the information it wants. Lean gives us a lot, but it also hides certain things. And if you know where these things are, you can go and get them. And your metaprogram can work, but they can be quite unfamiliar to most Lean users. This isn't boilerplate per se, right? So it's not like different metaprograms will necessarily do exactly the same thing to get this stuff, because there are multiple ways to do everything. So it's kind of bespoke plate, if you will. This access cost is related to whether there's API around it, but there is more to the story here. So we spend code in writing these programs just to expose a data surface to work on. That's not really the point of our program, but we have to do it to get it to be as powerful as we want. And the actual point of our program, its actual responsibility, becomes buried in the source code. That hinders readability and it hinders maintenance. So this is kind of the bad ending of the Goldblum dilemma for us, right? We wind up with many different bespoke tools, right? And at the top, you can see each tool starts with a sort of bespoke plate code to access these arcane things, and its extraction of these data surfaces might be fragile. And only at the bottom of the source code of the tool does it actually get to the desired functionality and its fulfillment of its responsibility. And that bit at the top is a large per tool contribution to maintenance burden. And each time we want to add a new tool, we need potentially new infrastructure. So it's important to note we're not here yet, right? We're still doing lots of things without having to be as powerful as the tools I'm talking about. But we do want to prevent this. So can it be solved? What we want out of the Goldblum dilemma is we want a way to do these really, really cool things without them coming back to bite us later. So let's return to our three bespoke tools. Wouldn't it be great if we could take the bespoke plate code, the arcane access, and the fragile extraction of data surfaces out of the top and put them all in one thing and have these tools relying on that one thing? So let me present for now examples of things you might be familiar with or might be learning about that embody this design. So the first aspect of this design that I think is relevant is the inner data surface, right? Syntax linter infrastructure takes in the syntax of your command, and it takes in the info trees, all of those artifacts generated. And from that, it's able to perform its actions. So by providing this data surface to all linters, right, the linters themselves don't have to worry about going and getting it. They don't have to, for example, like reread source and reparse the command. Normnum is a tactic for normalizing numbers. And the way that this is implemented under the hood is it matches expressions, and you're allowed to, when implementing some facet of normnum, you're allowed to recursively call normnum itself. So if you're, say, writing this normnum extension down here for the square root, the on naturals, you see this little eval curly brackets e. That e represents the expression that normnum is giving you, and that is your data surface in this case, as is the monad that this is operating in. You don't need to know what a monad is, but this derive nat right in the middle there, that lets us call normnum's extensions recursively. So that's another aspect of the data surface that normnum sees. So it's really good if this interface is stable, right? We don't want to constantly be adding things or removing things to or from this interface. But crucially, they also have an outer behavioral environment, right? So syntax linter infrastructure is very flexible. You can do almost anything in that you might do in the course of command elaboration. But the main use case is logging. Um, and in fact, you can't do certain things like adding declarations to the environment. So the outer behavioral environment is not everything, but it's pretty flexible here. And in normnum, you want to provide this normalized expression at the end of your extension and a proof that it's equal to the original one. So now if you look at this, this is maybe just refactoring, right? Are we, by sort of analyzing the data surfaces and the behavioral environments, are we really adding a useful concept here? And that's what these next two blocks are for. So the other thing that these two entities do is they have harness capabilities, right? So if you make a linter, you're not responsible in the writing of the linter for actually running it on every declaration, or on every command rather. The syntax linter infrastructure takes the linter you've written, and at that top of the file during initialization, it puts it in some reference so that it can get back to it. And in the course of elaborating every command, it has a specific spot at which it runs your linter. And your linter does not have to think about this at all. Likewise, normnum, all of the matching on expressions is handled by the tactic. You don't, the normnum extension can be written without thinking about matching at all. The next thing is extensibility, and this is really important. For syntax linters, it's really straightforward. You just call initialize add linter and then the name of the linter you've just written. And for normnum, it's attribute based, right? So you write at normnum and then the pattern, and you put that in front of your normnum extension, and now normnum uses it. So that extensibility means that new tools can reuse this existing infrastructure. We haven't just refactored a couple of things into one factor plus some other things. And we can call that a cotool. So this is the sort of phenomenon that we're interested in here, is how do we create structures like this, and when should we? They're good, I claim, because they concentrate the maintenance burden, right? They still have that bespoke plate code and the arcane access and potentially fragile extraction of data surfaces, but now your maintenance is O of 1 instead of O of the number of tools. You can just maintain the cotool. And because it's extensible, you get many small, modular, low maintenance tools. This does, of course, depend on setting up that interface correctly, such that the tools don't have to do much extra work. So let's recap. Okay, a definition. So a cotool is a system which many modular tools can be developed for. So it's extensible, tools can be added later downstream of the cotool. It's a harness, the tool doesn't have to think about when it's run. It provides that inner data surface, exposing a certain interface to the tools that they can act on meaningfully, and an outer interface allows them to take certain actions in a computational setting so they have certain powers. And optionally, it's nice if the cotool allows external control of tools, such as which tools are active, through that harness. So why the name? A cotool, the reason is that a cotool turns any tool into a computational occurrence at specific points in time, and emphasis on the any, right? So by analogy, covectors act on vectors to produce scalars. Cotools can be thought of as acting on tools to produce behaviors. So we can conceptualize a cotool as providing a receptacle or a harness into which tools fit. So there is one more line here. And if you've read the abstract of my talk, you might have expected the wrong thing. I'm talking about Lean Scout, which is something by Adam Topaz. This is a library for extracting data files from entire libraries. So you could run Lean Scout on Mathlib and get all the types, for example. And importantly, you get them in JSON. So it has the inner data surface, has the outer behavioral environment. You can write to JSON when you're writing your data extractor, and it's extensible. Your data extractor can be written downstream in your own library. You don't need to rely on Lean Scout's capabilities. But you do need to actually do the running in the tool. So is it a cotool? Should it not do this? And this is where we start thinking about interface tensions. what should go in the API and what should go in the cotool interface itself. Because sometimes you do just need better API. The one difference to keep in mind is the API is distributed among tools. So each tool has to use the API, but cotool functionality is centralized. It's automatically there just by using the cotool. So in contrast to API, cotool interfaces can become invisible for better or worse. Here are some useful questions to ask. I'm not sure how we're doing on time. So we can ask
You're halfway through.
halfway through. Okay,
I
great.
mean,
Thanks.
including your question time.
Right, exactly. All right, thank you very much. So here are some useful questions that we can ask when trying to decide, hey, do we design the system using sort of this cotool philosophy, or do we just need more API? So would absorbing the given API into the cotool interface make the cotool overly restrictive, for example? Maybe we don't want to use this API all the time. Does being able to actually see the API in use in the code help us understand the code? I mean, our goal here is maintenance, right? So if absorbing it into the interface actually makes it less readable in a certain case, we want to avoid that. So, or does having API complicate the code? That's possible too. Maybe having the API obscures the tool's actual purpose or responsibility, and winds up with the tools having lots of bespoke plate code. Maybe it elevates these arcane facts to the tool level. Like the tool shouldn't really be thinking about, say, task life cycles or some really low level thing, but the API exposes that. In that case, that increases the knowledge demand for maintaining the tool and makes it cost more for maintenance. There's also a chance that the API is something you need to call repeatedly, and it sort of spaghettifies the data flow and just gives you a really inconvenient data surface. So demanding, it also might demand many flags and settings that could instead be sort of atomic distributed actions in the right environment. So for example, when you run a syntax linter, you run it in this computational environment called command-labm, and that has loads of interfaces that let you just access different things. It's not the case that every time you want to do something, you need to pass in flags saying what you want to access exactly. So cotools take on and should take on the responsibilities of providing a stable interface to tools and running the tools. And we need to be sure that these are appropriate and that we give appropriate other responsibilities to the API, right? We do want to actually balance. We don't want to just say, yes, use cotools all the time. So should you make a cotool, right? So I think of cotools in a library as akin to city infrastructure, right? You might only have a few of them per library. And they can come with some cost, right? You actually need to make the extensibility capabilities. You need to make the harness utility. And they do introduce this balancing act, right? Even this stuff we're talking about needs to be figured out, right? What goes in the interface, what doesn't? And that balancing act is between the flexibility of tool behavior, right? Where tools can just do anything, which is kind of the state we're in, right? And maintainability of and ease of writing the tools, right? The less the tools can do, the easier it is to write because you've only got a few options. And a question you should ask is, can you stabilize the data surface that a cotool exposes, or is it actually in flux and you don't really know what you want yet? So some reasons that you should make a cotool and that it's nice to make cotools are that Lean already makes cotools really natural with attributes and environment extensions and initializable code. Lean is sort of extensible by default. And of course, cotools can help reduce the maintenance burden if done right. They can reduce footguns and enforce invariance on behalf of tools so that the tool doesn't have to worry about it, right? And more interestingly, less as a sort of preventative and more as an enabling feature. By allowing the tools themselves to be small and modular and easy to write, having a cotool helps us do more, right? Because we can make future tools with more functionality, more easily and rapidly. And we can allow innovation by other people at different points in the ecosystem. I mean, so imagine if only Lean Core could introduce linters, right? We would be quite linter poor. So what all this is for, it's not some new approach per se, right? This is meant to be a useful conceptualization. It's distinctive and it puts a name to something familiar that's easy to recognize in practice. We already have cotools, we just didn't know that they were cotools. But we really want to capture in this notion of a cotool that sense of modularity and that sense of having execution capabilities, which is not captured by simply saying refactor it. And more importantly, this notion of a cotool itself, just having that concept in your head, lends itself to thinking about and guiding library infrastructure, which is what we care about with maintenance. So this is the good ending, right? We have many small modular low maintenance tools. We have a concentrated maintenance burden. We have an extensible environment where new tools can reuse the existing infrastructure. And hopefully the interface is stable enough that writing a tool is a nice experience and not constantly changing. So cotool philosophy can help with the Goldblum dilemma, right? We can do really, really cool things with it and have a lower chance of having them come back to bite us later. And importantly, cotools are not just guardrails against them coming back to bite us, but they're also a means to have the first. So let me say a few words now on Skimmer, which is a project that I'm currently working on. Pictured here is a black skimmer, a kind of bird that skims the surface of the ocean and picks up fish. In our case, we're skimming the surface of the lean process and capturing this data, this info tree data, the syntax data, et cetera, et cetera. And I really wanted to have a live demo. And I told everyone that I was working on this with that I would have a live demo. And unfortunately, it just wasn't in the cards for me. But I did take screenshots. So take this as sort of a mock-up, or maybe better, a teaser for the kind of thing that I'm working on. Watch this space. So let's say we have a whole bunch of deprecated identifiers in use here, right? So in this case, we're deprecating a type. And we have that type in the name of many different declarations, and many different declarations use it. We should be able to go into a file in our library, write some commands, so refactor deprecated all, let's say, and type dive. And that will prepare, it'll ask us, do we want to prepare the following actions? Refactor deprecated all, and we say yes, okay, prepare them. So now prepared them, and it went through and computed what those refactors should be. It says prepared 6 refactors, one of which needs review. Apply refactors, we say sure, execute. So now we look at our file, and we've got all these deprecated aliases here. And if you look near the bottom, you see vector forward dot of fn instead of just vec underscore for fn. So we've also modified the source code that uses these identifiers. Now, what about that one that needed review? In this case, we have this little review term elaborator, right, that turns the previous term into the new term. It tries to elaborate the new term. And if it's successful, it tells you the generated term is successful. Successful, would you like to apply it? And you can click to apply it. In this case, what happened was we actually changed the root of the declaration. So it used to enable dot notation on arrays. Now it enables dot notation on strings. The automation didn't catch that. It put string dot append car array out front. And really, we would like to use dot notation again. So in this case, the review was helpful because we were able to keep it in the style we care about. So that's my talk. Thank you so much for listening. And thank you to everyone at the Math Initiative who has supported me, and everyone else in my life. Thank you.
Thank you very much, Thomas. Nice talk. And